So transversal relaxation is slightly different. Transversal relaxation, it's the time it takes for the projection of M0 on the XY plane, so no longer the Z, but the XY plane, also known as the transversal plane. The time it takes for the projection of M0 on the transversal plane to decay down to 37% of where it started from right after the radiofrequency pulse. So M0 is right here. You put in the radiofrequency pulse, essentially protons wobble their way back down into the XY plane. And then it's going to take a certain amount of time for the projection on the XY plane to shrink to 37% of where it started from. However, it's not because protons are wobbling back up. It's for a different process known as dephasing. So T2 relaxation or transversal relaxation is about protons losing phase with each other or dephasing as they wobble back up. Okay, so these are two different processes. Okay, let me show you a video because it's going to make things probably the clearest. So here are protons, and all together they're all pointing up. So all together they are creating an M0 pointing up. Okay, so M0 is pointing straight up. Now we're going to put in a radiofrequency pulse. Radiofrequency pulse. There you go. And you see that protons are slowly. They all start swinging together. They're all pointing together, and now they're fully inside the XY plane. Now the radiofrequency pulse stops. Look at the points of the various protons. See, they're pointing in slightly. They stop pointing altogether. See, they're no longer all pointing, all swinging together and pointing in the same place at the same time. This process of protons losing coherence of where they point to in the XY axis is known as dephasing. So protons essentially losing coherence in phase, in where they are in the phase. Okay, let me show this again. So here are protons. They're swinging freely inside B0. Radiofrequency pulse. You see that the protons are now now they're all in phase, right? They're all swinging together. They're all pointing exactly in the same place. Okay. Now we let go of the radiofrequency pulse. Look at the points. They slowly lose coherence, or they dephase. They're pointing at different parts in their phase. And then while this happens, they also wobble back up. It's just not shown in this video. Okay. Now, when protons are all together, M0 is strong, right? As protons dephase, M0 becomes weaker and weaker and weaker. That is transverse relaxation. As protons lose phase with each other, the strength, the net vector that they create becomes weaker and weaker and weaker. That process of losing strength is, because of dephasing, is transverse relaxation or T2 relaxation. So T2 relaxation is defined as the time it takes for the protons to dephase in the XY plane so that the net magnetic vector that they produce has gone down from 100%. Remember, when the radio frequency is in, as soon as they are at 90 degrees, they're all pointing at the same place. So that's 100%. As protons slowly lose coherence and dephase, their sum vector slowly shrinks. Once it has gone down to the time it takes for that to go down to 37% of where it started is called T2 relaxation. Let me show you a different video that makes this even clearer. So now you're looking at the protons from above. Okay, protons have been pushed down into the XY plane, and you are now looking from above to the XY plane. This yellow line that you're seeing here is the net, is M0, is all the protons are pointing all in the same place, and they're creating a big M0. And now we're going to let protons swing freely. There you go. Here. And you might notice that you see here these little lines. It's protons that are starting to dephase. Here, let's let it swing a little more. Hup. Oh no. Let's try this again. By the way, notice that the length of M0 is just about here, so it's further than the X. Okay, so here we go. Let's let it swing a few times. Okay, so look now. See, the length, you can already tell it's shorter than the X. Why has it lost magnitude? Because protons are starting to dephase. See these little lines here? These are protons that are no longer pointing all in the same direction. And as they fan out or dephase and stop pointing all in the same direction, the magnitude of M0 in the XY plane decreases. Let's let it swing a little more. Oh man, I hate this. I'm sorry. Okay, we're letting it swing, we're letting it swing, we're letting it swing. Right, and so here it is. You can see it's much smaller, right? Remember, we started that it was this, the magnitude was all the way up here. It's been swinging, protons are dephasing. See now, one proton is pointing here, this proton is pointing here, this proton is pointing here. So the net sum of all the protons is shrinking. That is T2. And off we go, and off we go, and off we go. And see, now, look, one proton is pointing here now, one proton is pointing here, one proton is pointing here, one here, one here. So their net magnetic field altogether has shrunk a lot from compared to where it started, which, as you remember, was all the way out here. And finally, all protons dephase, and essentially the projection, the strength of, the strength of M0 on the XY plane has become 0, because every proton is pointing in a different place. So if you add them all up, there's no net vector, there's no net projection on the XY plane. The time it takes for M0 to go from a strong vector, because everybody's pointing in the same direction, to 37% of that, because protons are dephasing, is called T2, or transversal relaxation. In other words, here you can see a depiction, a still depiction of it. When all the protons are swinging together, they give rise to a big signal. They have a big M0. As protons slowly lose coherence and go out of phase or dephase, the signal slowly shrinks. So this is really the magnitude of M0. It is the magnitude of M0 as protons dephase. All right? So 2 parts to relaxation. Longitudinal, the time it takes for protons to recover in the Z direction to 63% of where they started. And transverse relaxation, or T2 relaxation, which is the time it takes for M0 to shrink in the XY plane, in the transversal plane, down to 37% of where they started. So T1 is a recovery process. The projection on Z is growing. T2 is a decay. The projection on XY is shrinking. Now, here too, different tissues have different T2 constants. So, for example, there might be 2 different tissues. One tissue might take a certain amount of time, maybe just a few hundreds of milliseconds, to shrink down to 37% of where it started, and another tissue might take much longer. And see, in these parameters, the fact that different tissues take different amount of time to relax, both in T1 and T2, is what allow us to take pictures that have contrast across tissues. Just to give you some numbers, at 3 Tesla, protons and fat go out of phase down to 37% of the initial signal really, really quickly. It only takes 35 milliseconds. So fat is said to have a short T2 decay time, or a short T2 constant. At the opposite end, CSF, cerebrospinal fluid, has a long T2 constant in the sense that it takes 300 milliseconds for protons inside the cerebrospinal fluid to lose phase to a point where their net vector on the XY plane is down to 37%. As I was saying, the interesting part of this is that you can fine-tune parameters of the MRI machine to create contrast between different tissues. For example, let's say that this is one tissue, this is a second tissue. We can adapt the parameters of our MRI machine so that we can take a picture that maximally differentiates, I don't know, gray matter from CSF. We're interested in seeing gray matter and white matter and CSF as different things. That is called contrast. So remember, T2 is about protons losing phase with each other as they slowly realign into B. Now, what causes this dephasing? Well, a number of things. First, if you imagine my fists being protons, as they spin, they hit each other. And as they hit each other, they lose coherence, right? They hit each other, and now one is pointing one direction, one is pointing in the other. Another one is molecular diffusion. See, protons don't stay still, as in that video that I showed you. They actually diffuse in tissue. So this means that sometimes a proton will enter a different magnetic field. And remember at what frequency does a proton spin? Gyromagnetic constant times the magnetic field it's in. So if take two protons, they're spinning perfectly together. If one of the two suddenly were in a different magnetic field, it might start spinning faster, rather precessing, I should say, faster or slower. And so these two protons would lose phase quickly. So dephasing can happen for a number of things. As I said, spin-spin interactions, molecular diffusion. But the most important one to us is local field inhomogeneities. Again, take our two protons. If one of the two, if they happen to be in different magnetic fields, they will go out of phase quickly. Now, one thing that creates different magnetic fields at the microscopic level is deoxyhemoglobin. See, deoxyhemoglobin in it has some heme groups, which you can see right here, 1, 2, 3, and 4. And at the very middle of each heme group, right in the middle, right here where my cursor is, there's an atom of iron. And see, the atom of iron is there with two electrodes sticking out. And the reason it has two electrodes sticking out is that if a molecule of oxygen floats by, molecule of oxygen lacks two electrons. So if a molecule of oxygen floats by, that's the mechanism by which the oxygen will bind to deoxyhemoglobin, turning it into oxyhemoglobin. However, this means that if there's no oxygen attached to the heme group, these two electrodes are creating a local inhomogeneity in the field. They are distorting, those two electrons are distorting the magnetic field. Remember what I told you? Imagine there's a molecule of deoxyhemoglobin, actually, molecule of deoxyhemoglobin, and my fist is a proton. Right? The proton is now nearby some kind of magnetic distortion. So imagine you have two protons, one of the two, and they swing together, right? They might precess pretty well together. Now put nearby one of the two, a molecule of deoxyhemoglobin. It's paramagnetic. It changes the strength of the local magnetic field. So now my right proton will spin at a slightly different, will precess at a slightly different frequency. If these two protons are precessing at different frequency, do they go out of phase faster or slower? Think, talk. They go out of phase faster, right? Because they're no longer going at the same frequency. One of the two might be just a little faster. And so as they do that, they dephase quick. And I'll show you an illustration of this in just a moment, so you don't have to rely on squinting and look at my fists as I move them around in the air. Here's what I meant. So we have a number of protons in blue. Let's imagine that right here, there's a molecule of deoxyhemoglobin. And as I said, because of the iron inside the heme group that is unbound to oxygen, the deoxyhemoglobin is paramagnetic. So it's altering the strength of the local magnetic field. And maybe there are a few other deoxyhemoglobins lying around. Of course, nearby, there's also some oxyhemoglobin. Now, oxyhemoglobin is hemoglobin that has oxygen that is bound to the heme groups. This means that the iron atom is no longer there with 2 electrons sticking out and spoiling our nice 3 Tesla magnetic field. The oxygen has bound to it, and 2 things happen. A, they bind, and so the electrons are no longer, in a sense, exposed, but also a conformational change happens. The oxygen sort of pulls, kind of rotates inwards inside the molecule of hemoglobin and brings with it the iron nucleus. So oxyhemoglobin, so hemoglobin that has oxygen attached to it, is not paramagnetic. In fact, it's diamagnetic. It's neutral with respect to the magnetic field. So if a proton is nearby a molecule of oxyhemoglobin, it doesn't change anything. Right? And again, let's imagine there are molecules of oxyhemoglobin hanging around. So let's say this is the case. Let's put in our radio frequency pulse. Protons, our M0 goes from being straight into B0 to down in the transversal plane. We stop the radio frequency pulse. Protons start losing phase together. Sorry, start losing phase and don't swing together anymore. And we see the signal that we said earlier, right? As protons spin, they lose phase with respect to one another. Why do they lose phase? Several things. They hit each other, spin-spin interaction, they diffuse, or some protons happen to be nearby a deoxyhemoglobin, which essentially puts them in a magnetic field of a different strength. So the protons nearby, let's say the oxyhemoglobin, are inside a 3 Tesla magnetic field. The protons nearby a deoxyhemoglobin are inside a 3 Tesla magnetic field plus a tiny, tiny bit. What does this mean? Well, it means that the protons that are nearby deoxyhemoglobin are now spinning at a different frequency, are now precessing at a different frequency compared to the protons that are nearby oxyhemoglobin. Why? Well, of course, the Larmor frequency. Right? Protons spin gyromagnetic constant, which is the same for all our hydrogen proton friends in this picture, times magnetic field. And we just said that protons nearby oxyhemoglobin are in a 3 Tesla magnetic field. Protons nearby a deoxyhemoglobin are in something slightly different. What does it mean? It means that protons nearby oxyhemoglobin versus proton nearby deoxyhemoglobin will start going out of phase pretty quickly. So the strength of the net magnetic field, which you see pictured right here, will go down pretty quickly. Now, let's say that something happened. And so let's just say that this line here marks how strong the field is. Okay. Now, let's say that something happened, and we'll get to that in a moment. And in this part of tissue, there now happens to be much less deoxyhemoglobin than before. Instead of having 5 deoxyhemoglobins, we have only 2. What does it mean in terms of the magnetic field? Well, now it means that most protons are inside a 3 Tesla magnetic field. In fact, only the protons nearby these 2 molecules of deoxyhemoglobin are in a slightly different magnetic field. So what does it mean for the time it will take for protons to dephase? Are they going to dephase faster or slower? Remember, protons dephase for many reasons, including because of differences in the magnetic field, protons are swinging in their slightly different magnetic fields, which makes them go at different Larmor frequencies, which makes them dephase faster. If now there's little deoxyhemoglobin, more protons are in the same magnetic field. Now many protons are inside exactly 3 Tesla. Only a couple protons, those nearby these 2 deoxyhemoglobins, are at 3 Tesla plus something. What does it mean for M0? Well, if more protons are going spinning together at the same Larmor frequency, it means that they will spin more together. It will take longer for proton to dephase. So the signal at any given time will be stronger. It will take longer for protons to lose phase with respect to each other. So under this condition, with little deoxyhemoglobin, the signal is stronger. Okay? So if there's a lot of deoxyhemoglobin, it spoils the magnetic field. It makes everybody go at a slightly different Larmor frequency. And so, of course, protons will lose phase with respect to each other and dephase quickly. And M0 will shrink down to 37% real quick. If instead there's little deoxyhemoglobin, now all protons are kind of swinging all at the same Larmor frequency. If they're all going together, it'll take longer for M0 to shrink down to 37%. So the signal is now stronger. And the difference between when there is comparatively more deoxyhemoglobin and the signal is not very strong because protons dephase quickly, versus when there is comparatively less deoxyhemoglobin and the signal is a little stronger because it takes a little longer for protons to dephase or to relax in the transversal plane. The difference between these 2 conditions is known as the blood oxygenation level dependent signal. And this is the whole basis of fMRI. In fact, if somebody says, oh, I'm doing fMRI scanning, what they really mean is that they're doing bold imaging. They're observing when parts of the brain have changes in their level of concentration of deoxyhemoglobin. So bold imaging is a mechanism to see when concentration of deoxyhemoglobin increases or decreases. And see, what is interesting is that what is it that makes the concentration of deoxyhemoglobin increase or decrease? Well, neural activity. So in other words, this bold imaging is a mechanism to see indirectly when some part of the brain engages in neural activity, because when it does, the concentration of oxyhemoglobin and deoxyhemoglobin change. Specifically, and we're going to see this in detail next week, the concentration of deoxyhemoglobin decreases. So now we have a mechanism to see when neurons in some part of the brain are active. Because if some part of the brain becomes active, maybe as somebody inside an MRI machine engages in some kind of mental activity, we're going to see it. Because we are going to see the T2 signal get stronger. We're going to see the bold signal get stronger. So that's why we use fMRI in order to study the human brain as it functions. Because bold gives us a mechanism to see when a part of the brain engages in greater neural activity. So, as I said earlier, what causes transverse relaxation? Well, a number of things. We said spin-spin interactions. We said molecular diffusion. And we said local field inhomogeneities. And each of these has its own little acronym. Now, typically by T2 prime, local field inhomogeneities, in this field, we really mean deoxyhemoglobin. Now, interestingly, we cannot only see one of these three. When we do bold imaging, we're just seeing all three together. So that's why bold imaging is often referred to as T2 star weighted imaging, because what we see, the changes in the signal that we see, have to do with T2 and the T2D and the T2 prime. So the rate, the signal due to transverse relaxation is really a mix of all of these things when we do bold imaging. However, at the scale that you and I are looking at, so at the scale of understanding the human brain as it functions, really mostly only T2 prime is the one that changes appreciably. So even though we see all of these together, the only one that changes in the span of few seconds, the way we are looking at it, is typically only T2 star. So although we see all of these things together, the one that will change maybe when somebody starts performing a mental activity versus when they're not doing that mental activity tends to only be T2 prime. So we use T2 star as a way of looking at T2 prime.